Hi, let's continue our examples of metric spaces and the curves inside them. In the previous video, we went over examples that were built out of Euclidean subsets or Riemannian manifolds. Today, we see metric spaces that are not even locally any Riemannian manifold. We begin by a very general and useful construction of new metric spaces out of old ones. And one way of doing this is called the snowflaking of a metric space. If you give me a metric space with the distance function d, then raising it to any power between 0 and 1 produces another metric on the space X. So to prove this lemma, basically, all you need to do is that this d tilde satisfies the triangle inequality, because the symmetric part and also non-degeneracy parts are obvious. You only need to prove that d tilde also satisfies the triangle inequality. I'm not going to prove this. It's basically follows from the concavity or convexity of t to alpha function as a real valued function. We apply this to R1 with the metric x minus y, the natural metric on the space, and we raise it to power 1/2 to snowflake it. The new space we get is an interesting metric space with many properties that we won't get into. For example, its Hausdorff dimension is equal to 2, equal to that of the plane. And the thing is that points are actually very far away in this new distance. Remember that root h is much bigger quantity than h when h is pretty small number. And this distance is being really long is manifested in this proposition that, in fact, there are no curves of finite length other than the ones that are just constant. For this, I can give a short intuitive proof. Without much difference, actually, we can assume that you want to connect to 0 to 1. With other points, it's basically the same, maybe some shifting works. Now, if I have a curve that connects at time a, say, and again here without loss of generality, say gamma of 0 is 0 and gamma of 1 is 1, we can always parameterize a rectifiable curve in the interval 0, 1. We can also assume this gamma is Lipschitz, but we actually don't need it. So gamma is continuous, that's all we need. Because it's continuous by intermediate value theorem, every value here is actually covered by this curve. So there is some time where curve takes value equal to 1/n. And there is some other time where it takes value 2/10, and so on, until it n minus 1/n is covered. And this is not covered in a monotone way. I'm not claiming that it takes same amount of time to reach from one to the other. Nothing other than just what I'm saying. It's a continuous curve by intermediate value theorem. It covers all these values. Now, by definition of length, it must be bigger than the summation of distances of these values. Okay, and this is bigger than or equal to, well, distance between this point and this point is 1/n in the Euclidean distance, but in this snowflaked metric, this will be 1/√n. Now, how many of these do we have? We have n many of these, so that becomes √n. Now we've shown that length of gamma is bigger than or equal to √n, but n is arbitrary, so this must be infinity. That's the only value bigger than every root n. There may be some inaccuracies, but this was only a sketch and can be fixed. But that's pretty much what's going on here. So now we have an example of a metric space with basically no rectifiable curves. And not because this space is disconnected or not path connected. It is in fact connected, but every curve we take ends up having infinite length. Okay. Another interesting thing in these examples will be that we can use the metric derivative notion and the length formula to give alternative proofs of all of these. We have a separate video covering this important thing in metric spaces, but basically what we defined as the speed of a curve in a metric space. Remember that this is a metric space with no subtraction and norm. So the only thing is we have the distance. So t plus h, distance of gamma t from gamma t plus h, divided by h. And then we let h go to 0. Of course, we need absolute value. This is called the metric derivative of a curve. And the theorem was that Lipschitz curves are metrically differentiable almost everywhere. And moreover, the length of curve can be obtained from integrating the speed along the curve. So these were covered in that video. The way we prove this proposition using this is we prove quite easily that the speed has to be infinity whenever our curve is differentiable. And then it follows that length is also infinity because you're integrating an infinite function over a non-degenerate interval. So 2 proofs of this proposition. The next example is one built on the plane, but instead of having the usual distance using Pythagorean theorem, we look at the L1 distance or the taxicab distance. Many of you will already be familiar with this. So the way you measure the distance of 2 points is you look at the shortest path that the taxi can take to reach it. And the taxi respects this grid of the city, which is, say, built up of roads that go only left to right or north to south. And there is no path like this. That's why it's called a taxicab norm. It's also called Manhattan metric and many other names. But mathematical definition is just this. So whereas the usual one was this to power 2, and then you take power 1/2. That is the usual Euclidean norm, but this is the L1 norm. The claim is that there are infinitely many geodesics that join points that are diagonally from one another. So 0, 0, 1, 1. The claim is that there are infinitely many geodesics, many shortest curves going through here. One of them, as you might guess, has to be this diagonal. This one here also has the same length. And our claim will be that basically any curve that doesn't turn back, any curve that is monotone, will actually have the same length, even these ones that go up there. So the only way you can stop being a geodesic is if you turn backward, either on this diagonal, or you go here, you lose height and then gain it back, then these are not geodesics. So how does one prove this? The direct proof will be that because of this particular form of distance or norm, if we have a curve and these are the component functions of it, so you can also say gamma 1 is the shadow of gamma t, projection onto the x-axis, and gamma 2 is projection onto y-axis. Then the length of gamma through this summation of distances breaks up, because of the linearity here, into length of gamma 1 as a curve in R1 plus length of gamma 2 again as a curve. So gamma i's are curves from the same interval into R1s instead of into R2, and these are usual R1s because restriction of this metric to one of the axes agrees with the usual Euclidean one. So if you only look at one horizontal direction, this metric agrees with the R1 metric. And if you look at this vertical only, again, distances are the same as Euclidean R1 distances. It's only in the diagonals that you notice this difference. Okay, and from this, then you can deduce the fact that the shortest curve between these must have length 2. Because, well, gamma 1, let's draw our picture again. So both gamma 1 and gamma 2 are curves that go from 0 to 1. And this is gamma 1 curve. So it connects this to this. If your curve is not optimal, it may return back onto itself, and then it doesn't go monotonically. And gamma 2 does the similar thing. And the length of any curve in R1 that connects 0 to 1, the shortest curve is equal to 1. So this, if gamma is the shortest curve, then this becomes, well, let's do it. And if you're not a geodesic, if you're only a continuous curve, then this length is at least 1 and this length is at least 2. So we see that any curve in this R2 with L1 norm will have length at least 2. So anytime you find the curve with length equal to 2, that becomes a geodesic because you cannot be shorter. Now, how do we know that any curve that monotonically goes from here to here will be a shortest curve? Because if this is a monotone curve, then gamma 1 is monotone, gamma 2 is monotone, they don't return at any moment. Now, if you have any increasing function, not necessarily strictly increasing, but never returning back, then this length will be 1. And the same goes with the gamma 2 direction if you monotonically increase to that. So anytime you have a curve where gamma 1 is increasing and gamma 2 is increasing, you will have length equal to 2. And because you can never go smaller than 2, you figure out that this is an increasing curve. We can also argue similarly and claim that these are the only geodesics. And the argument will be that if it's not monotone, then either gamma 1 is not monotone or gamma 2 is not monotone. In that case, you get a strict inequality here, and therefore that gamma cannot be a geodesic. So yeah, a cool example of a space with infinitely many geodesics between two of its points. Similarly, we can prove this formula that length is summation of the length of projections using the notion of the metric derivative and this length formula, that this is integral of speed, and here will be integral of speed of gamma 1 plus integral of speed of gamma 2. So you can deduce this formula from this second one. So 2 implies 1, and 2 will follow from this quite easy fact that if gamma from an interval into R2 with L1 is Lipschitz, then if we forget that we have changed the metric in R2 and we go into the usual R2, then that gamma is also Lipschitz, because these norms are universally comparable by a factor of √2. So by Rademacher theorem, gamma prime exists. The usual gamma prime, like the velocity, not the speed, exists almost everywhere. And then you, this is even true in more generality of normed spaces, that when gamma is differentiable, Frechet differentiable, that means the usual velocity exists, then the speed, the metric derivative, is just norm, whatever norm you have on the space. So here we'll have L1 norm of this gamma prime of t. So L1 norm of the velocity will be the metric derivative. Now it's easy to see that if you have a curve, that if you have a vector which has 2 parts, so this will be gamma 1 prime at t and gamma 2 prime at t, then L1 norm, because of this, breaks up into 2 separate L1 norms. And so this becomes gamma 1 prime, the speed of first vector, plus the speed of the second vector. And now you integrate this equality, you end up with this 2. Sorry, it got messy a bit here, but that's a nice exercise showing how this metric derivative can be useful in a concrete example. Another consequence of this proposition is that the counter-Vitali function that we have seen before also, it's this strange function whose derivative is 0 almost everywhere, but nevertheless travels from 0 to 1. So this is 1, 1. Because it is monotone, the graph of this function as a curve, this is monotone. Of course, it's just the x coordinate. And this is the counter function, which is also increasing, not strictly though. But we saw that every time you had this, then the length of the curve was equal to 2. And this length we're talking about is this L1 norm. However, previously we had seen that the length of curve in this the usual norm was also equal to 2, although we never proved it. And this is the L1 norm. And that's just funny thing about this curve, that its length is the same in either metric. And that is basically because this graph, in fact, never makes any diagonal move. Effectively, it's only built up of up and right. And in this movement, we see that L1 agrees with L infinity norm. Yeah, something funny about this function. I think the nth funny thing about this function. And my last concrete example will be again R2, but this time with the maximum norm given by this. This norm is quite different. This time you actually have unique geodesic. All of these examples illustrate that things can be very different depending on the metric. Of course, when you change metric, you change the whole space from the viewpoint of metric properties. So this time, the only geodesic connecting 0, 0 to 1, 1 is basically just this diagonal movement. And here I have a quite satisfying pictorial proof. These were, both this and previous example were given as exercises in Ambrosi and Tilley's book. And yeah, these solutions I found myself and kind of was happy with them, especially with this one because I'm using nothing other than a simple geometric construction. So, okay, we can see that just from the definition of this length of a curve. Again, I'm writing a curve into R2 as with its component function. From definition of length as this sum over the pairwise distances of a partition, that this will be bigger than either of the length of its projections and length of gamma 2. You look at their shadows, and this length is bigger than these because, well, this is bigger than either shadow. Okay. Now, this shows us that because, well, gamma 1, the shadow, goes from 0 to 1 as a real valued function. So its length will be at least 1. The same goes with the other one too. So that length will be 1. On the other hand, length of this diagonal, if you parameterize the diagonal in the obvious way as a line, you can see that its length is equal to 1. You put partition points here, and distance of this to that is always equal to this length. Distance of this to that is equal to that length. Distance of that to that is equal to this length. It's only the horizontal increments that count, and when you add them up, you go from 0 to 1. So this shows, so on the one hand, lengths are never less than 1, and this one is 1, so the diagonal is 1 geodesic. Now our goal will be to show that there are no others, basically. And for that, I begin by showing that you have to, if you are a geodesic, then your image, your trace will have to be contained in the diagonal. So let me make my point. So here is the diagonal. My claim, if length of some gamma is equal to 1, which means if gamma is geodesic, then a gamma of the whole image of gamma is contained in this diagonal part, only between 0, 0, 0, 0, and 1, 1. So to prove this, if you have a curve and at some point it's off this diagonal, by symmetry, I'm assuming that that happens here. So that gamma of some value is inside here in this region. So I cut into 4 parts, and let's say gamma t for some value drops down to here. Then the length of gamma will be bigger than or equal to, now I take a 3-point partition. And the 3-point partition will be this point, which is gamma of 0 for A, the starting point. And this is gamma of B, the end point. And this is some intermediate value between A and B. Gamma of some T is between A and B. Now, when I take this 3-point partition, so this will be bigger than distance of gamma A. Let's give this a subscript T0 to emphasize that it's fixed, plus distance of gamma T0 and gamma of B. Now, the distance in infinity of this will be equal to this value here. Okay, so let's call this, I don't know, maybe A1. say d1 distance. So that's equal to this amount on the x-axis. Now the distance of gamma b to gamma 0 will be this increment here. Now notice that if from here to here added to from here to here equals 1, because let me do in green. So this green, this green thing here, from here to here, is equal to d1. Okay, and then that green part added to this little height here, okay, d1 plus this amount equals 1. Let me give this maybe d3. So d1 plus d3 equals 1. Okay, so because d1 equals to this green part, that's the point on the diagonal, and the remaining is d3 from 1. Now this guy is d2, so this is my d1 plus d2. So with d2, I mean the height difference between 1, 1, gamma of b, and this intermediate point that we had picked. We see that d2 is strictly bigger than d3 because you're in this region under the diagonal. So from these two, we deduce that d1 plus d2 is strictly bigger than 1. So this becomes strictly bigger than 1. So what I ended up showing is that if you are a curve where at some point you are off the diagonal, then your length is strictly bigger than 1. And that proves that you're not a geodesic. So let me clean up a little bit so you can hopefully see a more clear picture what is going on. Sorry, didn't need these. Yeah, I forget. There we go. So the point that started the trouble is this. This point is off diagonal. Therefore, when you write this 3-point partition, you get strictly bigger than 1 quantity. Yeah, so D3 was here. This is D2. Yeah, if this red was on the diagonal here, you would have D1 plus D2, because then D2 would be all the way that up. Okay, so if you have any questions about this, put in the comments as usual. Let's see. I want to end with a nice existing theorem about geodesics. So we saw examples both in Euclidean and in non-Euclidean setting that sometimes you have geodesics, sometimes you don't have them, sometimes they are unique, sometimes there are infinitely many of them. So it's of course very important to have general criteria for when we actually do have some geodesic. And this is a perfect example of such a theorem. If you are in a compact metric space, this is quite a lot to ask, but on the other hand, it's not that much of a restriction either. Then this problem, is there a shortest Lipschitz curve connecting x to y? Remember that if you're a rectifiable curve, you can always reparameterize it to be Lipschitz. Therefore, this is not a restriction. You can just replace it by rectifiable. Okay, if you give me 2 points in the metric space, then this problem has a solution. That means it has a minimum, not an infimum. That's important. That means there is one single curve which satisfies the minimality, as long as the set of Lipschitz curves connecting x to y is non-empty. Okay, so here's some stupid example showing the necessity of the last part. Let's say your space is built up of two separate pieces, still a compact metric space. Then between 2 points in different components, there is just no curve to begin with, so let alone minimizing. Therefore, we cannot bypass this. We have finite metric spaces, so as long as you can connect at least by one Lipschitz curve, then you can find the shortest curve. In other words, if you cannot find the shortest curve, it's because there are actually no curves connecting x to y. If you can connect x to y, then there must be a shortest that does this. For example, if we just put just a small bridge, and then there is some curve connecting them, and therefore there is a shortest curve connecting them. If we go back to examples we had, for example, one nice example was when we had the plane minus the point. So this point, just one point was missing. Then we had no geodesic between x and y. I mean, yes, we didn't have any geodesic between x and y if they were such that the shortest curve would actually need to pass through this. Because that point is not there, you have to make a loop around it, but you can always go into a smaller loop. Whatever you do, you can always do better. And we see that this theorem, it doesn't apply because we're not in a compact metric space. So you can go over all these nice examples and check where the theorem fails if there are no geodesics. Also notice that this doesn't guarantee uniqueness. The sphere or the circle with the antipodal points, there are more than one geodesics connecting them. So this is just an existent theorem, not a uniqueness theorem. And finally, its proof is based on a lower semi-continuity lemma and a sort of Arzelà-Ascoli. So what you do is the infimum, if you replace minimum with infimum, there is always a minimizing sequence. So that means there is a sequence gamma I from 1 to infinity such that these lengths converge to the infimums. Now the question is, can we build from gamma I one gamma where length of gamma, so if this infimum is alpha, such that length is equal alpha. If we can find this gamma, then definitely it becomes a geodesic. And this compactness is so strong that it allows some sort of Arzelà-Ascoli to prove that some subsequence of these converges to a curve in a stronger sense that it allows. Okay, so it okay, that's one thing. So these curves converge to one ultimate curve gamma. Now the lower semi-continuity part is that if gamma I is some sequence of curves that converge to another curve, the length of the limit will be no bigger than the limit infimum of the length of the ones in the sequence, which means the ultimate curve you find will always be shorter, and that's exactly pointing in the perfect direction for this. Okay, that brings us to the end of this video. Next, we'll cover the Hopf-Rino theorem and length spaces, a lot of cool stuff there too. Until then, watch my other videos and ponder a little bit about the delicacies involved in all of these spaces, play around with them. They're just nice puzzles. And make sure you subscribe if you have not done so yet. Thanks for watching this one too. Have a great day.